Electricity is the lifeblood of technological civilization and modern society. Without it, we would revert to the mid-19th century where you had no telephones, no television, none of the household appliances that you take for granted. Modern medicine would just be a fantasy. And due to the slow dissemination of information, science and technology would just grow at a snail's pace. But instead, with the discovery and harnessing of electrical forces and fields, we can view the arrangement of atoms. We can probe the inner workings of a cell. We can send a spacecraft beyond the limits of the solar system. And all this has just become possible in the last few generations of human life. A blink of the eye compared with the millions of years our kind spent foraging the savannas of Africa. Around 700, the ancient Greeks conducted the earliest known experiments with electricity, and it all began when someone noticed that a fossil material called amber would attract a small object after being rubbed with wool. If you've ever seen a lightning storm over the city at night, during the thunderstorm, you get a high concentration of electrical charge in a cloud, and it creates a higher than normal electrical field between the cloud and the Earth's surface. And this strong electrical field creates an electrical discharge, a big spark, as lightning. Other discharges you can see include cloud-to-cloud lightning or sometimes intra-cloud discharges. So in this unit, we're going to use the effect of charging by friction to begin an investigation of the electrical forces. Then we're going to discuss Coulomb's law, which is at the fundamental law of the force between any two stationary charges. The concept of electrical field associated with the charges is going to be introduced, and the effects on other charged particles is going to be described. And so at the end, we're going to discuss the Van de Graaff generator. We're going to see a couple of demonstrations using the Van de Graaff generator. To begin with, let's look at the objectives for this first part of our unit. The two objectives are that we want to be able to define what the unit of charge is and identify the basic carriers of positive and negative charge, and to discuss the concept of charge conservation and the role of experiments in early studies of electricity. So if you've ever used a plastic comb, you might notice that after you run the plastic comb through your hair, you're going to find the comb is going to attract bits of paper. And this attractive force is often strong enough to suspend the paper from the comb, and it's almost like it's defying gravity. The same effect occurs when you use other rubber materials like a balloon, for example, or glass. Experiments have demonstrated there's two kinds of electrical charge, which Benjamin Franklin named positive and negative. And by the way, that was just arbitrary. He could have named it muffler and Christmas card, but he named it positive and negative. And this atom here is going to demonstrate those different charges. You notice that in the center of the atom, you have this massive nucleus, which is composed of protons and neutrons. And neutrons are electrically neutral, but protons have a positive charge. Also, if you'll notice that the protons and neutrons have a lot more mass than these particles that are floating outside in this cloud, electron cloud, called electrons. Now, electrons are not very massive. In fact, if you notice, they have an order of magnitude 10 to the minus 31 kilograms, where protons and neutrons have a magnitude of 10 to the minus 27 kilograms. So protons and neutrons are much more massive than electrons, but protons and electrons carry the same magnitude of charge. They're just opposite. Most atoms are electrically neutral. That means they carry the same number of protons and neutrons together. We use the letter E to designate this charge. We call it the elementary unit of charge, which is 1.67 times 10 to the minus 19 coulombs. I'm sorry, 1.60 times 10 to the minus 19 coulombs. This is exactly the amount of charge on a proton and exactly the amount of charge on an electron. It's been experimentally determined. So the symbol E represents elementary unit of charge, and we say this is quantized because charge comes in multiples of this elementary unit of charge. Now, charges of larger magnitude than the charge on the electron or proton are built up by either adding or removing electrons. So as we mentioned earlier, that in nature, atoms are normally found to be neutral. That means they have the same numbers of protons and electrons. And by adding electrons or removing electrons from it, you can acquire a net charge. Now, something very important here is that because any electrical charge Q occurs in integer multiples of the elementary indivisible charges of magnitude E, Q being the charge, let's get a pencil here, Q being the charge, N being the number of charges, and E being the fundamental unit of charge, okay, we say that charge is quantized. In other words, it only occurs in multiples of this elementary unit of charge. So using this equation, Q equals NE, we can determine what the charge is on something. Let's take a quick example. So in our first example, how many electrons are there in 1 coulomb of negative charge? So we start by asking, well, what exactly is it that we know? Well, what we know is we know that we have a charge Q equal to 1 coulomb. And we also know that the elementary unit of charge is 1.6 times 10 to the minus 19 coulombs. So what we're going to do is we're going to solve this equation for N, or the number of charges. So solving this equation for N, we're just going to divide both sides by E. We know that the amount of charge is 1 coulomb, and we know the elementary unit of charge is 1.6 times 10 to the minus 19. When you divide, you get 6.25 times 10 to the 18 electrons. That's a lot of electrons in 1 coulomb of charge. So let's let you have a try. Is it possible for an object to have a charge of... So let's give you a shot at this. Is it possible for an object to have a charge of 7.04 times 10 to the minus 18 coulombs, and how do you know? So what I want you to do is to pause just for a second and see if you can figure this one out, and then we'll come back to it. Okay, so to solve this problem, we start with our basic equation. Q equals NE, and Q is the charge, N is the number of charges, and E is the elementary unit of charge. So in order for this to be true, in order for this charge to exist, if we divide Q by E, you have to come out with an even or an integer. So let's see, N equals Q over E, and we know that the charge is 7.04 times 10 to the minus 18 coulombs. And let's divide that by the fundamental unit of charge, 1.6 times 10 to the minus 19. And if you do that, you come out with the number 44. So 44 is an integer, so it is possible that you can have this charge. If we got a decimal, then it would not be possible because you can't have a part of a charge. So yes, this is possible. On this next section, I don't want to spend a lot of time since we are running behind a bit, so I'm going to go through this quickly. And this is just about charged objects and the electrical force. You know, electricity has a lot of applications that's come about because it's possible to transfer electrical charge from one thing to another. Now, usually electrons are transferred and the body either gains electrons or loses electrons. And the body that loses electrons gets a positive charge. The body that gains electrons is going to gain a negative charge. And remember that it's not very easy. In fact, we don't even talk about something gaining positive charges. Okay, we talk about them losing negative charges rather than gaining the positives because it's so difficult to pull those positive charges out of the nucleus. Now, the separation of charge occurs often when materials are rubbed together. Like, for example, if you rub a balloon against hair, you're stripping electrons off the hair and putting them on the balloon. Therefore, your hair gains a positive charge and your balloon gains a negative charge. I'm going to show you this later in a little FET demo. Also, if you take a glass rod and you rub it with silk cloth, then some of the electrons are removed from the glass and deposited on the silk, and it leaves the silk with a negative charge, and it leaves the glass with a positive charge. And there's many examples that you can use of charge separation. When you're walking across a floor, for example, you're scrubbing your feet across the floor, you notice you build up charge, and very often you become electrified and you reach out and touch a doorknob and it shocks you. Now, in a practical sense, electrical charges play a really an important role in many situations other than just rubbing two surfaces together. They're involved, for example, in chemical reactions, in electrical circuits, and radioactive decay, and the great number of experiments have verified that in any situation, the law of conservation of charge is obeyed. The law of conservation of charge says, during any process, the net electrical charge of an isolated system remains constant or is conserved. And another way of saying this is the amount of charge in the universe remains constant or remains unchanged. This is the law of conservation of electrical charge, and it's one of the most important conservation laws in physics. Another very important fundamental rule of charge is that like charges repel and unlike charges attract. So far we've discussed several basic properties of charge. Number one, charge is quantized. Number two, charge comes in two types, that's positive and negative. Number three, charge is conserved, which means the amount of charge in the universe remains constant. And four, like charges repel and unlike charges attract each other, which all of these make up the most important properties of charge. So that's going to bring us to the end of our first lesson on electrostatics regarding the properties of charge.